What you're looking at right now is a neural network, a tiny AI brain that's literally controlling physics in real time. All these hundreds of particles aren't really following any pre-written rules or subsets of rules. There's no move left here, spiral here, or any source of commands that's forcing them to do this. The AI is basically self-deciding and making its own decisions for every single movement it takes. So we see it's adapting, learning, and changing while you watch. So let me break down the code and exactly how I got to this from scratch.
Okay, so now let's talk about what a neural network is. So basically what a neural network mainly does, the main function of this, is that it will take in any digit of value, input value, put it into a machine, a computation machine, and that will just pump out a separate value. So in our case, we have two input values we're going to take in. We're going to feed in two values. So let's say we have our x position value, and we have our y position value. So this gets fed into our computation machine, and that will pump out two different output values. But this won't be f of x in this case. This would be how fast we move into x and how fast we move into y position. So how fast in x and how fast in y. Okay, so now let's talk about what weights are. So we can basically consider weights to be the knobs of the brain. So in this case, we represent weights as the initialization equation. We call this the initialization equation. So the way we can express this as a real equation, we could do W is equal or approximated to the normal distribution of 0 to sigma squared. So the value for sigma squared in this case is what we're mainly looking for, is going to be 1 over root fan in. Now you may ask what this fan in value is. Fan in is simply just our input value. So whatever our input value grid in the grid is, then that's going to be our fan in. So let's say our weight 1 is classified to be a 2 by 16. So our sigma value for this is going to be 1 over root 2. So that's basically 0.7, but we're going to just call it we're just going to use 0.5 in this case because we want it to be more conservative. So 0.5. And let's say our W2 value is 16 by 2. It's basically this flipped. And that turns into 1 over 4. And that's 0.25, and we can just round that to 0.3. So this entire process that we were just doing here, this is known as the Xavier's initialization. Now this is really crucial in LLM training as well, because the whole point of this function is to basically stop the network from exploding or flatlining before it even starts learning. So that would mean that if it's too big, then every neuron will start saturating immediately, and if it's too small, then the signal would just die before it even reaches the output. So this is a pretty crucial step. So now let's talk about the forward pass. So the forward pass is basically how the network is making a prediction on its own. So on the code I showed earlier, we see the forward x function is what it's doing is basically it can map any xy position to a velocity vector. So it could be dx dy, and that runs 400 times per frame. So each frame will just iterate 400 times. So for my layer 1, so the layer 1's objective was basically to expand into the hidden space. So that equation is h is equal to tan of h x times w1, or weight 1, plus b1, bias 1. So this is basically showing our x shape to be 400 and then 2, and our w1 already, we know our weight 1 is going to be 216 from previously, and our result of the h turns out to be 416. because we have the matrix multiplication involved as here. And basically what this does is every particle of x, y just gets combined with every weight, like over and over and over again. Okay, so now this was layer 1. So now let's talk about layer 2, where we compress back to the velocity. So our output function right here is defined as tan of h is equal to h times weight 2 plus b2. Now here in this case, our h is going to be 416, and w2 or weight 2 we already know is 16.2, and the result is 402. So a dx and dy for every particle is being formed here. Now the cool part about this is that we can squash this into one tan of hx function. So we can write this right here. So tan of hx, and this turns into the e to the power of z minus e to the power of negative z all over e to the power of z plus e to the power of negative z. Now what this function does is basically it sets a limiter and creates kind of a S-shaped graph. So like you can plug in any value like infinity, million, and it won't be crossing any like subsection point. It would be between -1 and it would be between 1. So we can visualize that real quick right here. So I'll just draw like a quick representation of the graph. So let's say this is 0.5, this is 1, negative 0.5, negative 1, negative 1, and 1. So point of inflection, we change right here. This constantly moves over there, and this constantly moves to the left. So as I said earlier, this the cool part about this function is basically no matter like what number you put in, as a million, infinity, could be anything, tan h squashes it down somewhere to be -1 and 1, and that's why this is S-shaped graph is being formed. Now the network can push as hard as it like wants, but particles can never really fly to infinity even if they try to, and the output of these two equations is always a velocity vector for every particle on the screen. So now let's talk about the train step function. So the first part of the train step function, which is actually going to be building the vector field. So this is kind of the place where the particles are going to travel. This is a free open space for them, and this is where they're going to be discovering and making their own decisions of which path to travel in and where the curvature is going to happen and everything. So this is pretty important because this is where everything is going to happen. This is the setting. So let's express this as an equation first, so it will be easier for us to perceive. So this turns into, actually this is a vector of v of x and y is equal to f theta of x and y, which is dx over dy. So it's simple differential equations. So this basically this right here, this little theta subscript means that the function is going to be dependent on the weights. So our weight 1 and weight 2 from earlier examples. So which that means is that if we change the weights, that means that's going to change the arrow in the field. That's going to change the direction. This is the part where it actually starts to get pretty cool, because the network is now going to start learning while it's running. Meaning that every frame we run, we run 4 training steps. So the key idea is basically going to be our loss function and how this is going to prevent it from running slow. So for example, let's say we're at point A, we go to point B, we go to point C, and we go all the way down to point D. Now this creates a pathway. Now let's say I'm at point D and I'm wondering, how can I get here next time much more efficiently with a less path load? So next time when I spawn at point A, I'm definitely going to be choosing a faster and a more efficient path road right here, and most likely computations are going to be faster because computations won't be run twice. The same computations won't be run twice. It will be completely new computations every single time. That's why the loss gradient function is there, and I'll explain it here in a bit. So let's first define this function and see the equation. So this is going to be f theta of x minus f theta of x plus epsilon squared. So this function is just saying loss is equal to the squared difference between the velocity at some point and the velocity at the same point that's being nudged by a tiny random epsilon amount value right here. And if those two values are very different, then the loss is going to be really big. And if the values are pretty small, then the field is going to be really smooth and fluid. So in gaming terms, it's going to be high FPS. Let's talk about why I added epsilon here. So we know that epsilon is estimated to be the normal distribution of 0 and the standard deviation of 0.05. So this is just a tiny random nudge. So basically the network is, as I said previously, is not going to see the same training example twice. It's constantly going to be tested on random pairs and random computations from their nearby points. Okay, so now let's talk about backpropagation. So this is our third step for the train step function. So now once we have the loss, the next thing we need to do is to figure out how to adjust the weights to make it more smaller. So the way we're going to do this is backpropagation. So this is actually built on a core concept from calculus called the chain rule, and that's what we're going to be implying right now. So first thing we're going to do is have d of loss right here, d of L. Yeah, let me rewrite this. It's not that neat. D of L over d of W is equal to d of L divided by d output times d output here over dh, which turns into dh over dw right here. So now we're going to be asking us, like, if I change this weight by a tiny amount, how much does the loss change? So how much difference will there be in the loss? We can't really compute this directly for every single weight, but something that we can do is, like, we can chain together all the simpler derivatives layer by layer and just kind of just walking backwards through the network. That's why we call it backpropagation. Alright, so now let's continue with our gradient step for the equation. So now let's set up our partial diff equation. So we're going to have this as the gradient of the loss with respect to the output. So we would have this partial diff of L and then V1 is equal to 2 V1 minus V2. So this basically correlates to our code, where the factor of 2 comes from differentiating the squared difference, and we divide the 32 because we're averaging like over a batch of 32 points, and that's basically just the mean. Okay, so now let's propagate the gradient back through the output layer and the weight update for W2 as well. So we'll have now the partial diff of L now divided by the partial diff of W2 is now equal to HT, this is the matrix form of the chain rule, times the same partial diff from earlier, L divided by V1, right. So now what this is doing is that the transpose of H1 times the output gradient, that's the chain rule in matrix form. So then we basically just subtract it from the W2 value and scaled by the learning rate, and then that's the extra form that we get. So that becomes 0.001 times W2. So this is called L2 regularization, and it's also called weight decay. So basically what this does is that it's going to add a penalty equal to the size of the weights themselves. So we differentiate that penalty and you get this term. So basically it like acts like gravity, constantly like pulling the weights back towards 0, so they can never spiral out of control over hundreds of frames. Okay, so now we need to push the gradient back through the hidden layers tan h. So we do need the derivative of tan h here. So let's get that real quick. So it'll be d over dz of tan h of z is equal to 1 minus tan h of squared z. So now already, like, since we already computed the h1 is equal to, tan h and then so on, we can write this basically as this right here. We're going to write the partial diffs again. So we can do L, partial diff of L divided by h1 is equal to L divided by v1 times the w of weight 2t, and that just converts into our partial diff of L and partial diff of z1 now, because we connected the equations. Of h1, yes. And then we multiply that by 1 minus the h1 constant from before. So h1 right there. Yes. And this also correlates to the line of code that's shown up here. And basically, like, what we do is first we pass the gradient backwards through the W2 using its transpose, and then we multiply the element-wise by like 1 minus h1 squared right here. So that's basically the tan h derivative, just evaluated at the hidden neuron simultaneously every time. And this kind of just tells us how much like hidden neurons like basically contribute to the problem. Okay, so now this is the final step. We have to have the final weight update for W1. So let's create the final weight update here. So partial diff of L and then partial diff of W1 is equal to x to the power of t times partial diff L again, and then partial diff of z1. Pretty simple. So it's basically the same pattern. We have to input the transpose times gradient and scaled by the learning rate, and we just add the weight decay like over and over. So the 4 equations basically are the 4 lines of code that I showed from each step, and that's basically the entire like brain being updated. It's basically just when all 4 of the weight updates will follow the same fundamental equation, the gradient descent. So what the gradient descent is going to do is basically have the W right here, our weight, and we'll just have weight minus our alpha constant times the partial diff of L divided by partial diff of W. So what this is doing is that W is going to get updated by subtracting a small fraction, the alpha constant, and the learning rate of the gradient. So basically, the gradient points will like uphill toward the higher loss. That means we go the opposite direction, like we go downhill. So we have to do this like around like 1,000 times, and the weight kind of just settles to a configuration that keeps the like field kind of smooth. And the alpha is basically always assumed to be 0.05, but in this case, I have it set to 0.005. Okay, so now let's talk about the physics behind the particles moving. So the last line here is the Euler integration. So the simplest way we can like solve this into a differential equation is that we could do dx dt and then set that equal to vx. Now position, this becomes position plus t1 is this x plus v of x, and then you have to multiply this by the delta of t. Right. I was gonna make this a dot, so it's simpler to identify. So yeah, delta of t. So now what this is gonna do is that each frame is gonna be one time step. So position is basically equal to this old position plus our velocity times the delta t. So we absorb delta t into a speed multiplier, so it just becomes position plus or equal to velocity. And every particle is solving this ODE every frame. So 400 particles, and there's going to be 60 times a second. So that's pretty good. It's pretty fast. Okay, so now let's also implement another theorem here. This theorem is actually pretty unknown to a lot of you. This was also pretty unknown to me. I had to research a little about this one. It's called the Brownian motion theorem. Yes. So we're going to be using that constant. So we see the position, we set the position equal to x, the old velocity plus this right here, v of x. And what we add additionally right here is the 2d subscript t, and where this new constant is actually the normal distribution of 0 to 1. So this is also statistic related. So the d is the diffusion coefficient basically. So here in this case, it's known to be 0.0008. It's a pretty small number. And without this term, particles are going to be like falling into perfect like repeating orbits, and it's going to look really mechanical and pretty fake. So this tiny noise basically just breaks the symmetry and keeps everything feeling really alive. We have the main logic down, the main engine down. So now let's also have a little bit of creative aspects to this. So we can talk about the trail decay and how it's fading. So the glowing trails are basically going to be considered exponential decay here. So it's pretty straightforward. So we have, it's that I of t sub t is equal to I initial times the wavelength to the power of t. Where the wavelength is equal to 0.965. This is the constant factor. So that means each frame every pixel's brightness is going to be multiplied by 0.965 after the t frames. And and after the t frames, it's going to be like 0.965 to the power of t. And the half-life for that is just going to be the time to reach half brightness. So we can set that equation to be t of 1/2 is equal to the log of 0.5 divided by the log of 0.965, which translates to 19.5. So basically just 20 frames. Okay, so we know that there's going to be about 20 frames or 2/3 of a second at 30 FPS. So this exact same equation describes the radioactive decay. Multiplied by 0.96, we have to lose 3.5% of whatever's left. And that's for every single frame. So the particle colors of speed mapped are speed mapped using Euclidean norms, basically Pythagoras in vector form. So if you don't know, that speed is simply equal to the vector magnitude, which is a squared plus b squared. Simply just that. So we just have to normalize that against the maximum speed of 0.012. You get a number from 0 to 1. And you have to feed that into your plasma color map and kind of just show the particles, like the glow deep violet, and the fast ones burn bright yellow white. And you're basically literally watching kinetic energy getting expressed as color. Because this is a really cool phenomenon to watch. And next up is going to be the actual simulation running in action.